Okay, in this video we're looking at the molar volumes of gases, and it's the idea that at 1 atmosphere and 25 degrees we have this much, or the volume of this box, gas. So 24.79 litres is the volume that 1 mole of any gas will take up at 25 degrees C and 1 atmosphere. It's actually 100 kilopascals, and 100 kilopascals is almost 1 atmosphere, and that is the pressure that is dictated by the Board of Studies that we have to look at in terms of molar volumes of gases. So it actually doesn't matter which gas we have. I could have H2 in this particular container, and once again 1 mole of H2 will take up 24.79 litres of gas at 25 degrees and 100 kilopascals. We could have Cl2 instead, and once again it'll take up 1 mole of Cl2 will take up 24.79 litres. We could have neon. We could have a mole of neon, and once again it takes up 24.79 litres. It does not matter what gas that we have at 1 atmosphere or 100 kilopascals and 25 degrees C, it will take up this volume. So these are the actual numbers that we're looking at. So at 0 degrees and 100 kilopascals, 1 mole of any gas occupies a volume of 22.71 litres. At 25 degrees and 100 kilopascals, 1 mole of any gas occupies a volume of 24.79 litres. Here we have a lovely gas jar with a lid. Now, this is 300 mils, or this has a volume of 300 mils, and I've just done a calculation over here showing the how many moles are found in 300 mil of anything, any gas at 25 degrees and 100 kilopascals. So this is the information that we've got. 1 mole equals 24.79 litres. So 1 mole occupies a volume of 24.79 litres. What I've done here, I've swapped it. So 24.79 litres equals 1 mole. I'm now going to divide both sides by 24.79 because that'll get me 1 litre. So 1 litre equals 1 divided by 24.79 moles. And then, because I've got 300 mils, which is 0.3 litres, I've got 0.3 litres equals 0.3 times 1 over 24.79 equals 0.0121 moles. So why have I bothered doing that? Well, that just tells me that in this particular container, say if that was full of oxygen gas, I would know that there would be 0.0121 moles of oxygen gas in there. Say if that was full of chlorine gas, it would have a nice yellowy shade, but again it would contain that many moles. If this was full of carbon dioxide, yep, you guessed it, 0.0121 moles. So 300 mils does, if I've got 300 mils at 25 degrees and 100 kilopascals, the amount of gas that's in there is 0.0121 moles. It does not matter what gas I have in there. Okay, here we have the 2003 HSC question to do with molar volumes of gases. First thing to do, write a balanced chemical equation. It's pretty straightforward. We've got ethanol, CH3CH2OH. I write it that way rather than C2H6O because it just gives an idea of the actual structure of the molecule, but you don't have to do it that way. Plus 3 oxygen is going to give 2 CO2 plus 3 H2O, including all of the states. Now, the mathematical calculations here. We've got 72.5 grams of ethanol was burnt completely in air. Calculate the volume of carbon dioxide that was produced at 25 degrees and 100 kilopascals. So 25 degrees, 100 kilopascals, we're looking at 1 mole being 24.79 litres. That's just straight on the data sheet. So the first thing to do is work out the moles of gas, the moles of ethanol, from using the 72.5 grams that we are given. So moles ethanol, we've got 72.5, we've got mass over molar mass. So we've got the mass 72.5 over the molar mass. So it's 12.01 times 2 plus 6 times 1.008 plus 16. One thing that it is important to note is that we have to use the complete number that is that is on the periodic table. So you don't round that off to 12, you don't round the 1.008 off to 1, you have to use the complete number that is in the periodic table that you are given. And you do that calculation and we get 1.57376 and some more numbers at the end. Now, the thing we need to do then is, that gives us just the moles of ethanol, we need to work out the moles of CO2. Now, if we go back up to this equation, we've got a ratio of 1 mole of ethanol to 2 moles of carbon dioxide gas. So that means for every mole of ethanol that is burnt, 2 moles of CO2 gas are produced. We worked out that the moles of ethanol is 1.57 blah blah. Therefore, the moles of CO2 is 2 times that. So this is the number of moles of ethanol. The moles of CO2 is going to be 2 times, and again it's because of this ratio here, it's 1 to 2. So we get 3.14752. We know that 1 mole of CO2 is 24.79 litres. Well, we've got 3.14752 moles, so we're going to go 3.14752 times 24.79. We get 78.027 litres. And we round that off to 3 significant figures. Why? Because I've got 3 significant figures here. So our answer is 78.0 litres. On to the 2004 HSC, and we have got a lovely little multiple choice question which takes a bucket load of calculations. So, ozone reacts with nitric oxide according to the equation. Alright, there's the equation. It's all 1 to 1. Alright, we're given 0.66 grams of nitric oxide, we're given 0.72 grams of ozone. Now, the problem is we don't know at this stage which one is the limiting reagent and which one is in excess. So that's going to be our first thing to do. Alright, we can work out moles of nitric oxide. So 0.66 over the molar mass, that's mass over molar mass, and we get that lovely number. Same with ozone. Moles ozone equals 0.72 over the molar mass of ozone equals 0.015. Now, therefore, the smallest number is 0.015, and again we're going all this 1 to 1 ratio. So I've got 0.015 for ozone, so ozone is our limiting reagent, and the moles of that will determine the moles of NO2 that is produced. Okay, and that's just a straight 1 to 1. So we can say, therefore, 0.015 moles of NO2 is produced. 1 mole of NO2 equals 22.71 litres. Therefore, 0.015 moles equals 0.34065 litres. And I'm not worrying about significant figures here. So if we look at it, if I go down the bottom here we go. We do our significant figures. We've got 2 sig figs, 0.34 litres. There is our answer, 0.34 litres, so it is A. Next question from the 2005 HSC. The student carried out a first-hand investigation to identify the relationship between the mass of a metal used in a reaction and the volume of gas produced. The first-hand investigation was carried out at 25 degrees C and 100 kilopascals, so once again there's our lovely data. So we're talking about 24.79 litres of any gas, taking up is the volume of any gas at that particular temperature and pressure. In each experiment, 200 ml of hydrochloric acid was added to some zinc and the volume of gas produced was recorded. The diagram shows the equipment used and the table contains the student's results. Alright, so this particular slide doesn't show anything other than the information given in the question. And there's our information. Our first deal was to graph the results. Okay, so we have a heading first off. We need to have a constant scale, which we do, lovely constant scale. And up here we need to have our axes labelled with our with the unit. So we're talking about mils here, mass of zinc in grams. Now, in terms of marking HSCs, they actually look at every single dot to make sure that they are in the correct place. Now, this particular result is obviously an outlier, so I have ignored it in terms of my line here. It's pretty much a line of best fit. It does go through all of the lines. Across here, I haven't put a line across here because it's obviously bottomed out there. We've reached our maximum amount of gas being produced, about up at this stage. If we look on the graph, it is this maximum amount is at 380 mil mark, which we'll use in the next question. So here we go. Predict the volume of gas that was produced in the experiment if 3 grams of zinc had been used and justify your answer. Okay, it's 380 mil, as the zinc is in excess. So we're having leftover zinc. The number of moles of HCl limits the amount of zinc that can react. So HCl is our limiting reagent. Any excess zinc has no effect on the volume of gas produced. Alright, next one. Calculate the theoretical volume of gas produced at 25 degrees and 100 kilopascals by the reaction of 0.56 grams of zinc with 200 ml of hydrochloric acid. Alright, with only 0.56 grams of zinc, all of it will react as per the results graph. Alright, so we've got zinc plus hydrochloric acid going to zinc chloride and hydrogen. That'd be the first deal, is to write an equation. You can work out the moles of zinc. So 0.56 over the molar mass of zinc, and then we get that many number of moles of zinc. Alright, the ratio is zinc 1 to 2 here. So, beg your pardon, 1 to 1, we're looking at the moles of hydrogen gas. So 1 mole of zinc, 1 mole of hydrogen gas. So the moles of hydrogen equals the moles of zinc, equals 0.008565. We know that 1 mole of H2 at 25 degrees and 100 kilopascals is 24.79 litres. Therefore, 0.008565 moles of H2 is going to be that times 24.79, which equals 0.212334 litres. And we have to take it down to one significant figure. Now, why one significant figure? Because we've got 200 ml here. Okay, 200 ml of hydrochloric acid. Now that is one significant figure. So our answer needs to be one significant figure. Okay, 2007 HSC. In 2004, Australia's Minister for the Environment announced that the allowable amounts of sulfur in unleaded petrol and diesel would be reduced over the next 5 years. Currently, as at 2004, sulfur in diesel is 500 parts per million, but it will be cut to 50 parts per million on 1st of January 2006 and capped at 10 parts per million from January 2009. So, calculate the volume of the sulfur dioxide produced when a full tank of 60 kilograms of diesel is consumed at 25 degrees and 100 kilopascals in November 2007. So November 2007, we're talking about 50 parts per million. All right, so that's from the 1st of January 2006 was cut to 50 parts per million, and 10 parts per million from January 2009. Well, we're not at January 2009, so we're talking about 50 parts per million. So sulfur at 50 parts equals 50 parts per million as at November 2007. Easiest way to convert ppm to just about anything else is to go 1 ppm equals 1 milligram per kilogram. Therefore, 50 parts per million equals 50 milligrams in a kilogram. All right, well, we've got 60 kilograms. So in 60 kilograms, there is 3,000 milligrams, which is 3 grams of sulfur. Okay, so then we can work out the moles of sulfur. We just got mass over molar mass, so we get that lovely number of moles there. We also know that 1 mole is 24.79 litres, again because we've got 25 degrees and 100 kilopascals. We've got our lovely equation here, sulfur plus oxygen going to give sulfur dioxide, so it's all just 1 to 1. Moles of sulfur equals moles of moles of sulfur dioxide equals moles of sulfur equals 0.093545, which is from here. As 1 mole equals 24.79 litres, that many moles equals that times 24.79 equals 2.32 litres equals 2 litres to one significant figure. Why one significant figure? Because we're using 60 kilograms. Next one, 2008 HSC. What are the volumes of 1 mole of argon and 1 mole of fluorine at 0 degrees and 100 kilopascals? Well, at 0 degrees and 100 kilopascals, 1 mole of any gas occupies 22.71 litres. Okay, so that's just a very basic question, so our answer is B. It doesn't matter what gas we've got. At 100 kilopascals and 0 degrees C, they occupy 22.71 litres. Next question. 1.22 grams of an unknown gas has a volume of 15 litres at 100 kilopascals and 25 degrees C. Calculate the molar mass of the gas. So, once again, 25 degrees and 100 kilopascals, we've got this information. 1 mole is 24.79 litres. I'm just dividing both sides by 24.79 to get to 1 litre. Therefore, we've got 15 litres, so 15 times 1 over 24.79 equals 15 litres. We've gone from 1 litre to 15 just by timesing both sides by 15. Therefore, we've got 0.60508 moles. Okay, therefore that many moles equals 1.22 grams. We're going to get to 1 mole, so we're going to divide both sides by 0.60508. So 1.22 divided by that equals 2.016 grams. So we've worked out the molar mass of that particular gas. Therefore, molar mass of gas equals 2.02 to 3 significant figures. Why 3 significant figures? Because this has 3 significant figures and this has 3 significant figures. Okay, identify the gas. The gas is hydrogen, H2, as its molar mass is 2 times 1.008 equals 2.016, which is the volume that we worked out there. The mass, I should say, the molar mass that we worked out there. Okay, another question. Here we go. Graph shows the maximum dissolved oxygen concentration in water as a function of temperature at normal atmospheric pressure. What is the volume of O2 that can dissolve in 10 litres of water at 25 degrees and normal atmospheric pressure? Alright, at 25 degrees, we're talking about 8 milligrams per litre. Alright, at 25 degrees, the concentration of oxygen, this O2 concentration, is 8 milligrams per litre. Talking about 10 litres. In 10 litres, there is 80 milligrams. 80 milligrams is 80 times 10 to the minus 3 grams. Moles oxygen is mass over molar mass. So we've got the mass over the molar mass. We've got that many moles. We know that 1 mole is 24.79 litres. So 0.0025 moles equals 0.0025 times 24.79 equals that. Equals 61.9 mil equals 62 mil when we round it. So our answer is A. Also a fairly convoluted question just for a 1 marker. Next one, 2010 HSC. A gas is produced when 10 grams of zinc is placed in 0.5 litres of 0.2 molar nitric acid. Calculate the volume of gas produced at 25 degrees and 100 kilopascals. Include a balanced chemical equation in your answer. So first things first, let's do our balanced chemical equation. Alright. Now, from the information they've given us, so we've got 10.0 grams of zinc. So moles of zinc was 10 over the molar mass of zinc equals that many moles. We know the concentration of nitric acid equals moles over litres, therefore moles equals concentration times our litres. So we have got 0.2, which is our concentration of nitric acid. We've got 0.5, which is our number of litres of nitric acid. So moles nitric acid equals 0.1. Now, ratio of zinc to nitric acid is 1 to 2. So, nitric acid is the limiting reagent, okay, because I've got 0.1 moles of this and 0.15 moles of that. If I've got 0.15 moles of zinc, I would need twice as much moles of nitric acid. So I'd need, 0.3 moles of nitric acid. I don't have 0.3 moles of nitric acid, 0.1. So that's why my moles of nitric acid is the limiting reagent. So, nitric acid is limiting reagent. 0.1 moles, nitric acid produces 0.05 moles of H2. Why? Because it is 2 to 1. So there's going to be half as many moles of nitric acid. Of hydrogen gas. So 0.05 moles of H2. 1 mole of H2 equals 24.79 litres. 0.05 moles of H2 equals 0.05 times 24.79 equals 1.2395 litres. Therefore, the volume of gas produced equals 1.24 litres to 3 sig figs. Why 3 significant figures? Because we have 3 significant figures here. We've got 3, we've only got 2 here. Only got 2 significant figures and 2 significant figures. So our actual answer should be to 2 significant figures, not as I've written it here. It should just be 1.2 litres. Okay, that's a bit more acceptable. 1.2 litres. Again, it's 2 significant figures because we've only got 2 sig figs here and 2 sig figs there. And our answer needs to be to the lowest number of significant figures that are in the question. onto the 2011 HSC. All of the carbon dioxide in a soft drink with an initial mass of blah was carefully extracted and collected as a gas. The final mass of the drink was blah. What volume would the carbon dioxide occupy at 100 kilopascals and 25 degrees C? So, the mass of CO2 that is released is just first number minus the second, so it's 0.63 grams. Need to have a grams in there. So, moles of CO2 equals mass of a molar mass equals 0.63 over 12.01 times plus 2 times 16 equals that number. We know that 1 mole of CO2 equals 24.79 litres, therefore 0.0143 moles equals that times the molar mass equals 0.355 litres, and the closest answer there is B, which is 0.35 litres.